Good day, my people. So last time we discussed something concerning renewable energy, and today we have to talk something again concerning power supply. You know, many people are talking. I've been saying so many things concerning power supply, and talking of so many things, and I'm talking of electrical isolation and magnetic coupling. So, and I found out that it is good for us to discuss something on that power supply issue, and also talk something concerning the working principle of transformer itself. Because for you to do a perfect and wonderful power supply, especially conversion from this AC to DC, you need to involve transformer so that there will be a perfect electrical isolation. So here, when we talk about the transformer itself, it will be pertinent for us to define transformer in electrical engineering or in any other science region. We know that transformer contains laminated copper winding or coil. Then you have soft iron that is also laminated. It's also a thin sheet. You have former that is in the transformer itself. So when you talk about a step-up transformer, you have to consider the number of turns of the loop, number of loops in the primary winding or the one in the secondary winding. So I define transformer as a static electrical machine that is capable of transforming voltage from one level to another level. So it transforms voltage. So if a transformer is stepping voltage up, invariably it's also stepping current down. That is why when you talk about the equations of a transformer, you talk about the relationship between the voltage in the primary side and the voltage in the secondary side. You see that their current relationship is inverse. They have inverse current relationship. So, but before that, we have to talk about how the electricity transformer is transforming, how it's being generated. For the generation station, we are made to understand that whenever a loop of coil is rotated, across a magnetic field, linking the loop, something will happen in that coil, because the magnetic flux that comes from the north pole linking the south pole of the magnet has something and that place is where you have strong magnetic field, and that is magnetic region. So whenever you cut that linkage, cut the flux, so there you have provided the relative motion between the loop and the north and south pole magnet. So this relative motion that has been created by you, mechanically created by you, will cause an EMF to be induced in the what? In the coil itself. So when the EMF is induced in the coil, you see that you can get it and use it. Okay? You can connect your load, the equipment you have in your house, you can connect them and the electric current will start flowing through them. So this is what Faraday told us. Okay, so when you talk about the laws of electromagnetic induction, talk about the Faraday's law that says that the EMF is induced, okay, in the coil is directly proportional to the number of turns, okay, with respect to that of change of magnetic flux with respect to time too. So the phi, the t. So time rate of magnetic flux changing is what Faraday was talking about. So, and that is still what is happening in the transformer itself. So the transformer is transforming voltage, okay, with respect to what is happening at the primary winding, and also transferring the same thing to the secondary winding. The same time rate of change of the flux is happening in the primary and also at the secondary. That is why a transformer has to work at a specific frequency. Okay, at a specific frequency. So if you derive the equation of number of turns and the EMF is induced, or the EMF is transformed in the transformer, you see that so many things are there. So, but when you still go back to the origin of the electricity, you now see that a relative motion between the loop of the conductors, which is the armature in our generator. So when you talk about AC generator, you talk about getting the slip ring commutator with a carbon brush in it. But the one you have now is self-excited electric generator that is connected to a mechanical prime mover. So the rotation of the armature is gotten from the machine itself. So when the machine rotates the armature and you have the stator there, so we now know that, you now see that the strong magnetic field at the stator winding linking the rotor itself will cause something to be induced in those wires at the slot of the stator. That is where you can get your current. So this is Faraday's law. And Lenz also said his own that the EMF induced opposes the motion that is producing it. So they have some experiment that gives something to such. So what we are interested in is just to know how the electricity we are using is being generated, so that when it's generated, you can now take it up, step it up and transfer it, because you want to put it into transmission line. So you have to increase the voltage, because when you are increasing voltage, I stated before that if you are increasing the voltage, invariably you are stepping the current down. Because if you don't increase the voltage and you want to take the current you want to take the power to a very far distance, it means that if the current is higher than the voltage, all the current will be lost along the transmission lines because of I square R. So as the voltage is going along the transmission line, then some current will be forming a lot of troubles in the cable. They may even burn the cable and everything will collapse. So the main thing you do is just to step the voltage up, because in any electrical network, what drives the driver in electrical network is the voltage. Current is being driven by the voltage. That is why when you talk about a potential difference, you see that there must be a gradient, potential gradient, so that whenever a connectivity is established, or maybe the network is closed, then the voltage will start driving the current from the region of higher potential to the lower potential. So from the live cable to the neutral cable. So electrons will start moving. So these are the things you see. So when you take it up to that level, before it reaches to the domestic houses, industries, and all those things, have to step them down. So the ones we use at home and for domestic use is out of a 240 volt. Like in this country, we use 240 volts, and I have a frequency 50 hertz. So I want to talk something on that of a power supply. So we have a transformer, as I've stated before. That transformer is a static electrical machine that is capable of transforming voltage from low level or from high level to any level you want it to be, depending on the number of turns in the transformer. And if you want to design the transformer by yourself, you can do it. There are so many equations you can apply to design your own transformer. But the only thing you need to know is that if you want to step down the voltage, know that the number of turns in the primary must be greater than the number of turns in the secondary. Okay? Then the gauge wire has to be reduced. The diameter of the wire that you use to produce the primary winding has to be reduced so that you can get more number of turns. Then in the secondary winding, you have to increase the wire diameter so that you get the voltage that is low, so the voltage will be stepped down, because at that secondary, the current will be stepped up. So if you don't use a normal wire gauge that is capable of carrying the current you needed at the secondary side of the transformer, then when you plug it, then the current that will pass through there will melt the whole thing there. So how did we get voltage at the secondary side of the transformer if there's nothing like electrical connectivity? That is what electromagnetic induction told us, and we want to discuss that now. So know that the AC we are talking about is alternating current. Alternating current is a current that is generated through a sinusoidal formation. It has a positive half cycle and a negative half cycle. So when you put it into wavic nature, you see that when the rotor is moving, okay, and in the region of magnetic field, there will be a point where the rotor will be at maximum. Okay, at maximum you get at 90 degrees, and now there's a peak voltage you get there. When it comes down to when it's parallel, it can come to the zero, then you can go down to negative maximum and still continue like that. So that is how alternating current is being generated. So this now shows us that the period of the current we are talking about is 1/50 cycles. So that is why the frequency is defined to be inverse of the period, as the period is also the inverse of the frequency. So 50 cycles per second is what we get. So when we talk about our generation, so that means that our rotor will rotate 50 times. Then we now know the frequency, okay, and it will be 50 hertz. So here we now see that the current we have gotten, which has been stepped down by the domestic transformers on the road, now comes into the house or where you want to use it. The 240 volts will enter into the primary winding of the transformer. Then because of the transformer core, you have what we call transformer core. Transformer core is a thin sheet of iron that is laminated. So that is a laminated core. So the core is there, the former is there. So once the changing magnetic flows passes through the winding, primary winding of the transformer, okay, that same changing magnetic flows, because we are meant to know that whenever a current carrying conductor, generates a changing magnetic flows. In the same way, a changing magnetic flows will induce EMF in a current, in a conductor that is not carrying any current. So the same way now, the conductor at the primary winding of the transformer does not have any current in it, but we have inputted or we have connected an alternating current at the primary winding of the transformer. So this alternating current will start to create a changing magnetic field. And remember, I stated before that there's no electrical connectivity between primary winding and the secondary winding of the transformer. So the changing magnetic flow that is created, okay, at the primary winding of the transformer generate magnetic flows. The electricity there generate magnetic flows because the electricity is alternating. So it has a flux around it. So the flux that is connected around it needs something. It will not pass through the laminated core of the transformer. So there is magnetic circuit. The transformer core, the laminated core, is the magnetic circuit that links the primary winding to that of a secondary winding. So in a transformer with electrical isolation, the coupling there is magnetic coupling, not electrical coupling. Some people are still making the mistake saying that all the transformers are electrically coupled. It is not true. Isolated transformers are magnetically coupled, not electrically coupled. Okay, so you see that the magnetic circuit is the laminated core of the transformer, which will now transfer the magnetism that is being created by the primary winding of the transformer, carrying alternating current or changing current. Okay, so that same magnetic circuit that passes through the side of the secondary winding will now induce EMF at the secondary winding. So the EMF induced at the secondary winding depends, the magnitude of the EMF depends on the number of turns at the secondary winding. So since we want to step down the voltage and also increase the current, so we have to reduce the number of turns at the secondary winding, so that when the changing electric field comes into the winding of the primary winding, it will also create the same changing magnetic field and passes it across to the secondary winding, and also the same effect will induce EMF in the secondary winding. So you now see that if you have the EMF in the primary winding, which is directly proportional to the number of turns in the primary winding multiplied by the rate of change of magnetic flows. The same thing is also at the secondary winding. That EMF at the secondary winding will also be equal to the number of turns at the secondary winding multiplied by the rate of change of flux. So when you look at it, you now see that the rate of change of flux is the same at the secondary winding. It's also the same at the primary winding because of the frequency we stated before, that at a constant frequency, all these things are the same. So when you now say the EMF in the secondary divided by EMF in the primary will also be equal to the number of turns in the secondary multiplied by the time rate of change at that of a secondary over the number of turns at the primary multiplied by the time rate of change also at the primary. So if the time rate of change at the primary is equal to the time rate of change at the secondary, that shows that the frequency is constant, which is 50 Hz. So at this now, you now see that they will cancel out, and you have your EMF at the secondary over EMF at the primary will be also be equal to number of turns at the secondary over number of turns at the primary. Then with all these things, the current in all these things are inverse relationship, not direct relationship. So you can now have your current, which is the current at the secondary over current at the primary. So inverse relationship. So because when we are stepping voltage, or we are stepping down voltage, we are stepping current up. That is the inverse relationship. So you now see that you have finally produced the step down voltage that you want. If you want 240, if you are connected, if your transformer is connected to 240 volt and want to get 24 volt, you have to measure the area. You have to get your former, get the transformer you want to use, the laminated sheet, measure it, measure the former, measure the area, multiply your area and make it to be in what, a meter square. So the area you talk about is just 2 dimensions. Getting the length of the and the width of the core, multiply it together, you make it to be meter square. If it is cm that you use, convert to meter. When you divide the cm you got by 100, you go into meter. You multiply it together, you get the area. So there are some equations you will use. We have where you get the main thing is for you to get the turns ratio. So the turns ratio in a transformer will be 1 over 4.4 as a constant, multiplied by the magnetic flux density, which is 1.2 Weber per meter square. Then you also multiply by the length and the width, which is area of the core, of the former, and also the frequency. So if you are able to do all these denominator, multiply all of them, and use one or take inverse of it, you get the turns ratio. If your turns ratio is 2.2 volt per turn, that shows that if you have 240 voltage at the primary winding, the input voltage, you have to multiply the 240 voltage by the turns ratio you get. Then you now know the number of turns you will get at the primary winding. Then if you need 24 voltage at the secondary winding, you also multiply by the turns ratio. You still get it because it's still the same core that will carry both the primary winding and the secondary winding. So you now see that production of all these things and manufacturing them is very easy for you. So we now, when we talk of, you know what we are talking about is a power supply. We have discussed something on generation of electricity, the principle and working on so many things behind that. How the electricity comes into your domestic use, how it enters into a transformer that does not have any electrical connectivity but magnetic connectivity, and how the voltage is being created at the secondary winding. Then when you talk about the power supply itself, it is a process you pass, okay, by conversion of the voltages to get the direct current that is needed. Remember what we started with alternating current. An alternating current is a current that goes on the negative, positive side to the negative side. When you draw a sine wave, you see that the positive side is the negative side. So there's no specific polarity for alternating current. That is why it is called alternating current. So when something is alternating, okay, you catch here to be positive. When you come there to see the positive again, you will not see it. What you see there will be negative. And all these things happens at a very fast, it is very fast. To the extent that you will not even notice the blinking of the current itself. So But what we want is just to get a steady current that we may even use to charge our cell phone, charge our batteries, charge so many things. So because you can't use alternating current to charge some of those things. When you do that, they will be charging and be discharging. At the end of everything, the whole situation becomes worse. So that's why you need to put in some normal things and things that follow the rules and get what you want. So I'll talk something. I will discuss on the full wave rectification, where you use 4 diodes. The 4 diodes are connected when you have a square, and you have two sides of a square. So, but diode is just an electronic device that is used to conduct electricity, and it allows current to pass only in one direction. So it is a conductor when it is a perfect conductor when it is forward biased, and also a current blocker or a resistor when it is reverse biased. A very high resistive material, unless if the avalanche this thing is broken, or maybe the reverse bias region is broken, so it will start conducting. But that is abnormal conduction, because at that time some of the components in the circuit will start crying, because currents are now allowed to go where they are not supposed to go. So at the secondary winding of the transformer, where you get your 24 volt alternating current, it's still alternating current at the same frequency. Yes, the 24 volt there is still alternating. It still has the same frequency without a 240 voltage at the primary winding. So what do? You arrange your diode so that 2 of the diode will capture the electricity at the positive half cycle, and then also at the negative half cycle. If you get the diode and align them, the mixture where you have cathode and anode will be where you connect your AC. Just get the diode, join cathode and anode, 2 diode. Get another 2 diode, join cathode and anode. After joining cathode and anode, then use the 2 diodes, join them together again. So you now see that after the joining, you have where you have cathode anode, you have anode, and cathode. Cathode are the negative side of the diode. That place junction is where you get your high potential terminal for DC current. That is where you get your positive DC voltage. And the other side where you have anode is a ground. That is your low potential region, 0 volt region. So if you're able to align your diode in this formation, why do you use full wave verification? You use it for you to capture the AC when it has positive half cycle, and also when it has negative half cycle, because the polarity will be changing. When you get your transformer, you get your positive. Before you know what is going on, the positive is not there again. The positive will go down while the negative will go up. So the